we're going to draw the molecular orbitals for C2, and then we're going to draw the molecular orbitals for the C2 2- ion. So I've already drawn out the atomic orbitals for 2 carbons. We're showing all the atomic orbitals. Carbon has 6 electrons, and we're showing 2 of them. And we're going to now show the molecular orbitals. So we're going to draw our bonding orbital, antibonding orbital, another bonding orbital, antibonding orbital. So this is going to be sigma 1s, this is going to be sigma star 1s, sigma 2s, sigma star 2s. All of those orbitals are going to be populated with electrons. Okay, now is when it gets interesting, because we need to know what order are we going to put the bonding and anti-bonding orbitals on the p levels. Okay, so carbon, as I've said before in a previous video, boron, carbon, and nitrogen have what is called a large 2s 2px interaction. Okay, so what that means is the pi is lower. So we're going to put the pi from the 2p, that's going to be lower than the sigma 2p. All right, and then it's always the same for the antibonding. We have the pi star always lower than the sigma star. But when you have a large 2s 2px interaction, that's the pattern right there. And I told you, bacon, pi comes first. So remember, a large bacon pie would be something that I might order at a restaurant, if there was such a thing, because I love bacon. Okay, and then always the pi star is lower. Okay, so this is the tricky part, and you have to correlate that with the fact that we have a large 2s 2px interaction. If we were doing oxygen and fluorine and neon, that is a small 2s 2px interaction. So sigma comes first. Okay? With a large interaction, pi first. Okay, so got to remember that. Okay, so let's put these orbitals together. I've got 4 electrons to put in here. So 1, 2. Those are degenerate, so we half fill them first. Then 3, 4. So those are our electrons. Let's figure out our bond order. Did we get everything here? 2, 4, 6. 2, 4, 6, that's 12. So we have 2, 4, 6, 8, 10, 12. Okay, so let's get our bonding orbitals in blue. And then our anti-bonding we'll do pink. And let's figure out our bond order. So that's going to be 1/2 the bonding electrons, 2, 4, 6, 8, minus 4. Okay, so 8 minus 4 is 4 divided by 2 equals 2 bonds. All right, so now what I want to do is kind of clear things up here. And now we're going to look at this ion. So I'm going to go ahead and copy all of this since we've already done it. And then I'm going to shrink this down so we have room for our other version. Okay. So it's going to be C2 2 minus. What does that mean? That means we're adding 2 electrons. I'm going to add those in red. So 2 minus means 2 extra electrons. 1, 2. Okay? So that's going to put us here. So that gives us 2 more bonding electrons. So this is going to end up with a triple bond. So our bond order is 1/2. So how many total electrons do we have that are bonding? 2, 4, 6, 8, 10. And we're going to subtract the same number as with the C2 molecule. That's 4. So 10 minus 4 is 6. Half of that would be 3. So that's a triple bond. So which has the higher bond energy? It's going to be, in this case, the ion, C2 2 minus. Longer bond length. Well, the lower the bond order, the longer the bond. That means the bond is longer and the atoms are farther apart from each other. So it's weaker when the atoms are farther apart. They're not held together as tightly. So the longer bond length is going to be C2. Higher bond dissociation energy. The higher one is going to be the stronger. It's going to take more energy to break that. So hopefully you can see how to determine when you're given 2 different species of the same atoms, how to determine who has the higher bond energy, the longer bond length, and the higher bond dissociation energy.